Hi there, I am Dr. Motoshi Manna, and today I will discuss the quantum mechanical idea of particle in a box. This is a completely hypothetical situation where the particle is constrained to move in a finite region of space between two infinitely high walls. In classical mechanics, the motion of a macroscopic particle is governed by Newton's second law, force is equal to mass into acceleration. We can predict the future state of a macroscopic object from the knowledge of its present state. For example, if we throw the ball and solve F is equal to ma, we can predict its position and momentum at any point of time, and from that we can derive any other information about the system like its velocity, energy, and many more. But the classical mechanics fails to correctly describe the behavior of tiny microscopic particles in motion, and for that we require quantum mechanics. The works of Max Planck and Albert Einstein have established the wave-particle duality of light. De Broglie extended the idea of the wave-particle duality to matter and postulated that the matter has wave-like properties. The wavelength of a matter wave is equal to Planck's constant divided by the momentum of the particle. This was de Broglie's PhD thesis, for which he was awarded the Nobel Prize. For macroscopic objects, the wavelength is negligibly small, and so they can be considered only as particles. But for tiny microscopic particles like electron, the wavelength is of atomic dimension, and thus electron exhibits a significant wave-like character. For macroscopic particles, we can accurately specify its position and momentum at any point of time, but due to wave nature of a microscopic particle, its position and momentum cannot be simultaneously measured with arbitrary high precision. There is always an uncertainty associated with the measurement. This notion is summarized as Heisenberg's uncertainty principle. The uncertainty has nothing to do with the accuracy of the measuring device, but it is the fundamental property of the nature. So the quantum effects arises from the wave nature of the microscopic particles. Now the question arises, at what is actually waving, or what is the mathematical expression of that wave? To deal with, physicists postulated the existence of a wave function psi, which gives a complete description of a quantum mechanical system and thus also called the state function. Now the psi is obtained by solving the Schrödinger's equation, which is the fundamental equation of quantum mechanics. This is the time-dependent Schrödinger's equation, which determines how the quantum mechanical system evolves with time. This H cap is the Hamiltonian operator, or the total energy operator, consists of kinetic energy and potential energy. This is the time-independent version of the Schrödinger equation, which gives us the stationary state wave functions. So what the wave function tells us? Max Born interpreted wave function as probability amplitude. The magnitude of psi square tells us where the particle is likely to be. The solution of Schrödinger equations also provides us with the allowed energies of the particle. In the particle in one-dimension box problem, we will solve the Schrödinger equation for the translational motion of a particle confined in a one-dimensional box. We will see how the solution of this simple problem leads us to the illustration of several important non-classical features of the quantum mechanical system, such as quantization of energy, natural occurrence of quantum number, and the existence of zero-point energy. Though seems physically unreal, the exact solution of the simple and idealized solution helps us to interpret the behavior of more complex naturally occurring systems. We will see how this crude model is applied with some success to the pi electrons of linear conjugated hydrocarbons. In the next video, we will learn about the wave functions and their properties. So let us start with the translational motion of a free particle in one dimension. So let us consider a particle of mass m moving along x direction in absence of any external force. Since there is no external force, the potential energy Vx is constant for any values of x. And therefore, this is an obvious example where the potential energy does not depend on time And so the stationary states can be obtained by solving the time independent Schrodinger equation, which is minus h cross square by 2m d square psi x dx square plus Vx psi x equal to E psi x. So this is kinetic energy, this is potential energy, and this is the total energy of the system. Now for our convenience, let us consider that Vx equal to 0, and therefore this equation becomes minus h cross square by 2m d square psi x dx square equal to E psi x. Upon rearranging, we get d square psi x dx square plus 2m E by h cross square psi x equal to 0. Now let us consider that this term is equal to k square, and also we consider a trial solution of psi x, which is equal to e to the power alpha x. So substituting both of this value in this equation, we get d square e to the power alpha x plus k square psi x equal to 0, which is equal to alpha square e to the power of alpha x plus k square psi x equal to 0. So k square alpha square plus k square psi x equal to 0. Now psi x cannot be equal to 0, because in that case particle will be nowhere. So therefore two linearly independent solutions are psi 1x is equal to e to the power I kx and psi 2x equal to e to the power minus I kx. General solution of this linear second order differential equation is psi x equal to c1 e to the power I kx plus c2 e to the power of minus I kx, or we can write that psi x is equal to a cos kx plus b sin kx, where this c1, c2, a, b are arbitrary constant. So from here we have k square equal to 2me by h cross square. So rearranging that, we have E is equal to k square h square by 2m. Substituting it with its value h by 2 pi, we get E is equal to k square h cross square 8 pi square m. So we can write E, as E depends on k, we can replace E with ek. And the corresponding wave function that we get is psi x is equal to a cos kx plus b sin kx. Again we replace psi x with psi kx. Since there is no restriction regarding the magnitude of x, wave functions are acceptable for all values of k. Here again we can see that the energy depends on k square. All non-negative energies including 0 are acceptable. Thus the translational motion of the free particle is not quantized. As you see on the screen, these are the solution so far we get for the translational motion of free particle in one dimension. Now let us operate the linear momentum operator, which is p cap x, which is equal to minus I h cross d dx on psi 1x and psi 2x separately. So operating p cap x on psi 1x, we get minus I h cross d dx e to the power I kx, which is equal to minus I square h cross k e to the power of I kx, that is h cross k psi 1x. Similarly, if we operate p cap x on psi 2x, we get minus h cross k psi 2x. So this psi 1 corresponds to the eigenstate of a particle moving along the plus x direction with the linear momentum of h cross k, whereas psi 2 corresponds to the eigenstate of a particle moving along the minus x direction with the linear momentum of minus h cross k. So therefore, in either of these two states, the linear momentum of the particle is precise, but the position of the particle is not specified, and this is completely in agreement with Heisenberg uncertainty principle. The free particle problem is physically unreal because it is not possible to have a particle which does not interact with any other particle in the universe. Let us restrict the above particle between two length segment x is equal to 0 and x is equal to L. Now within this region, the potential energy is 0. That is, particle experience no potential energy, whereas outside the region, the potential energy is infinity. Therefore, the particle is always trapped inside this region and it never acquires enough energy to jump out of this region. So this can be considered as an example of ideal gas molecules moving freely inside the container. Now let us divide this space into three regions. Say region 1, 2 and 3, and solve the Schrodinger equations for each of these three regions separately. So say for region 1 and 3, which is located for s less than 0 and x greater than L, that is outside the box. We know that the outside the box, the potential energy Vx is infinity, and therefore the Schrodinger equation becomes minus h cross square by 2m d square psi x dx square psi x is equal to E psi x. Upon rearranging, we have square psi x dx square equal to 2m by h cross square infinity minus E psi x. Now infinity is much larger than any other term in this right hand side, and therefore this part become infinity this, or psi 1 or psi x equal to by infinity d square psi x by dx square, or simply equal to 0. So this implies that outside the box there is no probability of finding the particle because the potential energy is infinitely large. Now for region 2. That is located within this length segment x is equal to 0 and x is equal to L, which means that this region within the wall, here we know that for this region the potential energy Vx is equal to 0, and thus the Schrodinger equation becomes minus h cross square by 2m d square psi x by dx square is equal to e psi x d square psi x by dx square plus 2me by h cross square psi x equal to 0. Again, if we replace this quantity with k square, we get d square psi x dx square plus k square psi x equal to 0. Now this is exactly same as the translational motion of free particle in one dimension, which we just have discussed, and therefore we know the solutions are. So the energy equal to n square h square 8 pi square m, and the wave function is equal to a cos kx plus b sin kx, where this a and b are arbitrary constants, and for the confined motion of the particle in one dimension, we will apply boundary condition to determine the value of a and b. Let us see what are the acceptable solutions. So if we plot psi x as a function of x, we know that outside this region psi x is equal to 0, so we can represent psi x as a horizontal line along this x-axis. Inside this region, psi x has the form like this. This cos function and sine functions are, we know, oscillatory. So let us consider a wave function which looks like this. Now in this case, if we approach from the left hand side, there is a sudden jump or discontinuity in the value of psi x at x is equal to 0. Similarly, there is another discontinuity in the values of psi x at x is equal to L if we approach from the right hand side. According to the laws of quantum mechanics, psi x must be a continuous function of x, and meaning that there should not be any sudden jump or discontinuity in the values of psi x. So psi x must be continuous in order to be acceptable. So as psi x is 0 outside the box, in order to be continuous, psi x must be 0 at x is equal to 0 and also at x is equal to L. Therefore, the wave function, so therefore instead of this, the wave function should look like this. The application of boundary condition implies that only certain wave functions will be acceptable. So let us apply this first boundary condition at x is equal to 0. So psi 0 is equal to a cos 0 plus b sin 0 equal to 0. Now we know that cos 0 equal to 1 and sin 0 equal to 0. Therefore, we have a equal to 0, and putting a equal to 0 in this equation, we have psi x equal to b sin kx. Let us apply the second boundary condition. So psi L is equal to b sin kl equal to 0. Now b cannot be equal to 0. In that case, psi x will be 0 for all values of x and we will have an empty box. Therefore, sin kl will be equal to 0, and this condition is satisfied when kl equal to n pi, where n equal to 0, plus minus 1, plus minus 2 and so on. This n is called the quantum number. the choice of n is equal to 0 is excluded because this will again make psi x equal to 0 everywhere, which is not acceptable. The negative values of n do not provide us any new solution. They will only change the sign of the sine function. So now substituting the value of k is equal to n pi by L. In this energy expression, we have E is equal to n square pi square h square 8 pi square m by L square, or E is equal to n square h square 8 m L square, where n equal to 0, 1, 2, 3 and so on. As E depends on n square, we replace E with En. The wave function corresponding to En is psi n equal to b sin n pi x by L, where n equal to 0, 1, 2, 3 and so on. We still need to determine the value of this arbitrary constant b, but before doing that, let us look into the energy levels of the particle inside the box. Let us look into the energy level of the particle in a box. We have seen that the energy level of a particle in a box is equal to En is equal to n square h square by 8m L square, where n equal to 1, 2, 3 and so on. The particle can have infinite numbers of acceptable solutions and stationary states depending on the quantum number n. The figure shows the lowest 5 energy levels of the particle. Now, a very interesting feature of the energy expression is that all the terms in the right hand side of the equation are either constant or an integer. The Planck's constant h, the mass of the particle m, the length of the box L are all constants, and the quantum number n is an integer, which implies that the energy of the particle is quantized. The particle in a one-dimensional box can have only discrete energy values depending on the quantum number n. This is in striking contrast to the classical results that allows a dynamic particle to have any non-negative energies. The quantization of energy arises due to the boundary condition that the wave function psi x must satisfy in order to be an acceptable wave function. This is a general property of quantum mechanical systems. At the time of Planck and Bohr, the quantum numbers were introduced in an ad hoc manner. But in quantum mechanics, there is no mention of whole numbers or integers, but it arises naturally as a consequence of boundary condition. For example, the number of nodes of a vibrating string is an integer. Another very interesting feature of the figure is that at the lowest energy state, that is at the ground state, the energy associated with the particle is non-zero and it is equal to E1 equal to h square by 8m L square, corresponding to n equal to 1. This lowest kinetic energy of the particle is called the 0 point energy. The existence of 0 point energy implies that the particle is never at rest even at 0 Kelvin. The particle at least possesses this lowest and non-zero amount of energy which is irremovable. If there is no 0 point energy, then the kinetic energy and hence the linear momentum of the particle is 0. If the linear momentum is precise, according to the uncertainty principle, the particle's location will be completely indefinite, which is not the case as the particle is certainly present between x is equal to 0 and x is equal to L. Therefore, the occurrence of 0 point energy is in accordance with the Heisenberg's uncertainty principle. The concept of 0 point energy again is in striking contrast with classical mechanics, which allows the particle to be at rest inside the box. The separation between two successive energy levels E equal to n plus 1 and En is given by the following equation. The separation increases with increasing quantum number, as we can also see from the figure. The separation also decreases as the box length increases and is negligibly small when the box length is of macroscopic dimension. The separation between energy levels becomes 0 when the walls are placed infinitely far apart. Thus, the atoms and molecules in normal laboratory-sized container seems to absorb energy continuously, and their translational energies are not quantized. If the walls of the box are removed, then there will be no force acting on the particle and the particle is free to move along x-axis. From our earlier discussion, we know that the translational energy of the free particle is not quantized. Thus, the quantization of energy is a consequence of the boundary condition. For example, if an electron bound to a system has quantized energy levels and translation of electron between energy levels leads to discrete spectrum. In contrast, a free electron moving without any restriction has continuous energy spectrum. On ionization, an electron lost by an atom or a molecule is free to move without any restriction, which qualitatively explains the occurrence of continuum in the atomic or molecular spectrum. Let us see how the model of particle in one-dimensional box can be applied to linear conjugated hydrocarbons. For example, let us consider butadiene, which is a conjugated hydrocarbon that has 4 sp2 hybridized carbon atoms. Each carbon contributes to 1 electron to this delocalized system referred to as pi system of the molecule. For simplicity, if we assume butadiene as a linear molecule, then the pi electron of butadiene can move along a straight line from one end of the molecule to the other, similar to a free particle in a one-dimensional box. The model is called free electron model. The length of the molecule can be treated as the length of the box, which we can calculate as following. The allowed energy levels of a free electron are given by En equal to n square hs square by 8ml square, where n equal to 1, 2, 3 and so on. Butadiene has 4 pi electrons. According to Pauli exclusion principle, maximum 2 electrons with opposite spin can occupy a given state. Therefore, 4 pi electrons of butadiene will occupy the first 2 energy levels as shown in the figure. Upon interaction with electromagnetic radiation, 1 electron can move from n equal to 2 to n equal to 3 state. We can calculate the energy associated with the transition as following. From Bohr frequency condition, delta E is equal to h nu, we can calculate the frequency and hence wavelength of such transition. For butadiene, the theoretically calculated wavelength using the particle in a box model is 4.54 into 10 to the power 4 centimeter inverse, whereas the experimental value is 4.61 into 10 to the power 4 centimeter inverse. Therefore, we can see that the very simple model can be somewhat successful in explaining the absorption spectra of butadiene. This model can be extended to ring systems like benzene and called perimeter model. You can yourself try to estimate the wavelength of light associated with beta carotene from its ground state to the next higher excited state and compare with experimental value. So summarizing, we have seen how application of quantum theory to translational motion reveals the origin of quantization and many other non-classical features of quantum mechanical system. We found that the translational energy levels of a particle confined to move in a finite region of space are quantized. In the next class, we will discuss what are the acceptable wave functions associated with the particle, what are the properties of those wave functions, and how we can predict the probability of finding the particle at different places in the box. So thank you very much for listening and see you in the next class.